Hey guys, thought we should take a look at threads. Side note before I get going, I'm not going to worry about this assignment as far as one that you have to do to get credit. Feel free to do it. I think it'll be a good way to expand your abilities, and it's very useful knowledge. If you are missing an assignment, if you do this one, I will let it be where you don't have to do one of the other ones. Maybe that'll help you get caught up if this one's a little fresher and a little different, and those other ones are stale, and there's maybe a reason you haven't done them yet. Anyways, this one can only be a benefit to you. Anyways, side note, this is not Dr. Pepper, it's water. I haven't given up Dr. Pepper. I'm just alternating between Dr. Pepper and water. Okay, so I'm going to take you through an example where we're going to do some threading, and then we'll try to break up a workload where we can utilize threading. In fact, I'll do exactly what you're going to need to do is where you can decrypt something. Okay, so, well, let's change it. All right. Okay. Okay. So ignore this method right here, but I have a program with a blank main, and I want to do threading. So the basic idea of threading is you need to make a thread. So you can actually say thread T is equal to new thread, and you can say T dot start. The thing is I don't have any control over what thread is and what it's going to do. So what I can do is I can extend thread and tell it what I want it to do. So that's what we're going to do. So we're going to make a custom thread that will extend thread. That's it. You can construct it however you want. In this little toy example, I have a start and a stop for numbers I want to print out. But you could do whatever you want. If you want a website to go and check on, you can give it a URL. If you want to, whatever you want to do, you can construct this thread. Basically, the way I usually think about this is this thread's going to do some work. What information do I need for this thread to be able to do its work? In this case, I'm going to print from start to stop, so I need to know that information. So the instance variables in this case will be what you need to know to get your work done. And then you're going to have a method called run. It's not called start. There is a start method in the thread class, and whenever you call you can call it, but that whenever it gets done doing all of its magic to like fork its process and all that stuff, then it will call the run method, and this function will be running in that separate thread. So there's a few different ways you can extend a thread and do stuff, but this is the easiest, cleanest way, where you just have a run method, and you could do whatever you want in here. I'm going to print from zero. I'm going to print from start to stop, whatever those numbers are. Anyways, there we go. We got a custom thread. Bam. So I'm going to come up here, custom thread T. We're going to construct a custom thread. We'll tell it to start at 0, stop at 10, and then we'll tell it to start, and that's it. So it prints 0 through 9. So that's just a really complicated way to get this to run this method down here. And anyways, and that's not really multi-threaded. Actually, this is multi-threaded. I'm starting 2 threads. When you come into the program, you're in the main thread, and that thread, whenever it exits, your program's over. But that thread can, as long as it lives, it can spool off as many other threads as you want. It's possible to make threads be detachable where they can live on past the main thread, or sometimes they need to be subservient. There's a lot of different thread models depending on what language you have. And I'm not up on my specific Java threading libraries, but this will get you most of the way. Just make a new thread and tell it to start. All right. I can make another thread. I'm actually going to make both threads and then start them after the fact, because initiating them might be a slow process. So I want to make sure they do all their initiation and then I'll start them. What I'm trying to do is I'm trying to make it where you can see that the two threads are going to interweave. So one of the slowest things you can do whenever you're programming is to ask the computer to print something. And so if I'm printing 0 and then the other one wants to print 10, one thread is going to ask the system, hey, print 0 for me, and it'll be waiting around and just spinning on the CPU, wasting lots of time while this other parts of the system, not the JVM, but Windows itself, will be getting around to actually printing it for you. So anyways, you can use those extra cycles by just having another thread and not sitting around waiting. And so there you go. I can print all that stuff out. So you can see 0, 10, 1, 11. This is almost perfectly interweaved until here. It's not always going to be perfect. And you can't count on that. That's the whole point of threading, is so they can all kind of go off and do their own thing. What was I going to say? Now, one of the big gotchas for threading, and I'll tell you what it is, but I'm not going to solve it for you. And you're not going to need to solve it either. But one of the biggest problems with threading is a problem called concurrency. Concurrency is where you have different threads want to access the same thing. So let's say you have an array list. Let's say that's how you decide to store all the things that you have to work on. So you want to factor this really large number, and you have an array list of all the different number ranges that you might want to send off. And you go and you take one of those things out of the array list whenever you want to get it to work on. And so in theory, you could have this custom thread, you don't give it anything, and they go out to some common data structure and get information for work to be done. That is possible. You can do that, but pretty much whenever you have one thread mess with something that another thread might be able to mess with, you have to put protections in place. And there's about 3 different ways that Java can do that. One is you can put a lock on it. Number 2, and I'm not going to show you how to do a lock, but basically you say, hey, well, in this region of my code, I'm going to accept a lock, and then anybody else that's trying to do that will say, hey, is there a lock on this before you go into that part of the code? There's another easier way, but not quite as flexible, called synchronize. You can put that on a method, and you can just say, hey, this method is synchronized. And what that means is only one thread can be in that function at any one time. So a synchronized function can't have multiple people calling on it. So if you have a data structure that might have multiple people writing to it, you can make a function that can do the writing to that data structure, and that's the only place you write to it, and then you synchronize that function. And that's a pretty easy, lightweight way to do it. The other way, which I believe Java has, other languages definitely do, is you can have specific thread-safe data structures. And they make their functions where they're called atomic. They have atomic operations. Atomic operations are operations that you can't divide. So basically, when you call on this function, all other threads can't do anything while that's doing a thing. Anyways, you can do that efficiently depending on your language. Other times it can really bog you down and cause some bottlenecks. So what we're going to do is we're just going to ignore all of that, and we're just going to tell each of our threads at go time, this thread you handle this thread you handle that. And then whenever they coordinate back and want to give the information back, I'm not going to worry about that. We'll just print to the screen. That technically is also a potential bottleneck. But in our case, if we're trying to crack in some encryption or factor some large number, that's going to happen so rarely that there'll be no bottleneck on that. Like in this example that I did, it's potential if you have, like, you're printing like really large, big things, it might print really weird. Like you might have part of one string that you're printing inside of another string that you're printing. And it's possible to actually get corruption where you actually get bad characters, I believe. Or maybe they fixed it since then. But at some point in the past, Java was able to, printing is not 100% thread safe. It's pretty safe. So anyways, we're not going to worry about it. Anyways, so there's that. So anyways, know that concurrency is the problem. So you can imagine that one thread's trying to pop one element away from the array list, and another thread is trying to get something from the array list. So it's potential that one array gets an element while the other one's popping out that same element. So one person's working on something that doesn't even exist in the array anymore. So that could lead to bugs in your code later. Or imagine that, it could even be worse. You could just like completely corrupt and like get entries that don't even belong in your array because you have two sets of functions messing with things at the same time, and they all have the assumption that they're the only ones working on it. So like whenever you're doing linked list or whatnot, there's like all these different like wiring things you have to do. You could imagine if just two people are trying to do all that together at the same time, things will just explode. So you can get corruption with concurrent problems. So know that that's a problem and know that I'm willfully ignoring them. So my solution is just to break up the problem before I send it to the threads. That's it. Okay, moving on. So I got concurrent. I got two threads running. I have a down here at the bottom. I have two functions, encrypt and decrypt. I put it in a utility class. So those methods will let me encrypt and decrypt messages, and you can specify a key. And I have one other utility function. Maybe I'll put it down there. And I want to be able to take an int or a long and be able to turn it into a string. Let me show you that one, and then I'll explain why I want to do that. So okay, so that is crypt util dot string from int, and I'll give it some roughly long number. I don't know. I might have to print it out. Okay. All right, so there you go. I get not a random, but I get a string of characters. And so what happens down at this function is I take some number and I mod it by 95. That happens to be the number of characters that are usable in a key. If you look at the ASCII table, there's 128, but a lot of those are form feed and line feed and tab and stuff like this. These are the ones that you can actually use, like space and asterisk and A through Z and all that stuff. And then I add 32 because that's where the very first one is. That's a space. So anyways, I get the ASCII code for a number. And I add that to my output, and then I divide by 95. So I keep on taking this number, and essentially I'm turning it into a base 95 number using all 95 characters in the ASCII table that are usable as actual characters. So anyways, there you go. What I'm going to do is I'm going to have a secret message. I'm going to have a random key that I don't know, and I'm going to see if I can crack that key. That's it. So that's what I want the threads to do. So first things first is I'm going to try to get, I'll generate random numbers bigger and bigger until the time for one thread to crack it is I don't know, 10 seconds. Anyways, we'll do some experiments here. And then I will see if I can up it, and then break it off into multiple threads and see if I can keep my performance, or increase my performance anyways. One side note on performance. So if you have a task like this that is highly parallelizable, right now my computer, which is actually like kind of a mid to low range CPU nowadays, it's a dual core machine that has 2 threads per core. So I essentially have 4 logical cores. And anyways, each of those things, so right now whenever I run something in Java, it's going to use one of those cores. And so if I just have 4 threads, I could potentially go 4 times faster. I think you can actually go faster than that because each of those threads could get bottlenecks themselves where they just sit there waiting around. And so you could benefit from having even more than 4 threads if there's some kind of bottleneck within each thread that causes it to like go out to the system and ask for a file or download something from the web. So you can actually benefit from more threads than you have logical cores, so you have backups to kind of jump in there and do something while the machine's just waiting. Now, it's not always smart to run your machine at 100%, but most modern machines are fine at running at 100%, and they'll thermal throttle and do whatever they need to do to get the job done. So, all right, so let's go try to make a problem. So first, let's get I can encrypt something. Okay, so encrypt, so that's cryptutil.encrypt, and I can give it a message. The squirrel has landed. All right, so just some kind of message, and then I need some kind of key. And this is where this is going to come in. So I'm going to generate some random number. Import, I think it's, let's see, random r equals new random, random dot rand long. I don't know. We're going to go look it up. Java random. All right. So random is in util, so I've already imported that, so that's good. All right, and then I want to specify a range. There's a next long. Tell you what I'll do. I'll say next long, and then I will mod that by whatever number I want. Whatever. So I'll start small. So we'll say long key size. So in this case, key size really is going to refer to how many different key possibilities I'll consider. So if I say 10, it'll generate some number between 0 and 9, and then I'll use that to generate, in that case, one character. Anyway, so it won't take any time to crack that at all. So if I say a billion, it'll give me a billion different possible keys I have to pick from. So I'm going to start right away at, well, I'll do 1E9. I don't think it's going to like this. I don't think I can do the 1E notation. I have to actually put zeros. 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay. Put an L at the end so it knows it's a long. Okay. And then I can put, I'll call this my key, and put the key here. Save this as my encrypted message. And then print that out to see if that works. Key size. Oh, what is it not like? New capital R. All right, can't find symbol. We don't have that one anymore. Okay. Anyways, so here we go. This is a base 64 representation of the byte string that you get whenever you encode this. So whenever you encode it, you're going to get numbers that go the whole range of bytes, but you can't print that out very easily. So sometimes you need to send it somewhere. And so you change that byte stream into a base 64 representation. And base 64 is the easiest way to send things. Just a little side note on base 64. Base 64 has the numerals, the uppercase, the lowercase. If you add all that up, you get 62 characters, and so you'll notice a plus in here, and there might be a slash in here somewhere. Anyways, these are characters that can go in query strings on web pages. So they make sure all the characters are safe to be able to put in a query string. So anyways, it just makes it a little bit more portable. Just another side note, each of these characters doesn't really represent 1 byte. In fact, I think it's like 3 bytes equal 5 of these characters or something like this. And so there's like a correspondence. And then sometimes you'll have, you have sets of, well, I'll just go look it up. Base 64. All right, here we go. So you have, if you're in this case, if you're encoding the word man, so you have those 24 bits. You're going to get these 4 base 64 characters, so T, W, F, and U. So basically, you take those 24 characters and you're going to separate those into 4 chunks of 6, or sextuts. Anyways, that's what base 64 does, and you only use the alphabet, the uppercase, lowercase, and the numbers, as I mentioned earlier. And the characters, you can see that there's a plus and a slash, and then at the end there's padding. So sometimes if you take sets of 3 characters, maybe you only have 1 character, and so these are all zeros, and so you might have to pad this out to get it to work. Yeah, so like say the M turned into two letters, and then these don't need to be anything, so you could pad them, or whatever 0 represents, you could put those there. But anyways, blah, blah, blah. Anyways, here we go. That's the base 64 I have. Okay, so I don't know what that key is. I'm not printing that key. Well, let me just go grab it. So here is a message that I would like to crack. Okay, so I'm going to take that and all right, string encoded is equal to that. All right, so if I gave you that and I told you that the key was, you know, up to one, well, normally I would say it's like 5 characters or 6 characters and you have to try all the possibilities. In this case, though, we can just sequentially go through and try key 1, key 2, key 3, which corresponds to some set of characters. So anyways, so I don't know what the key is, but I will have to sequentially go through them. So all I have to do to go through all of those is this might be way too slow, but I'll say for long I equals 0, I less than the key size, I plus plus. So we're going to go through all of those. I will get a key. And if I have a key and I have the crypttext, then I should be able to say string message is equal to, and I should be able to decrypt this. All right, of course that may or may not work, right? I mean, only 1 in a billion chance of that working, right? So we can just try to do that. And the way I have it set up is if you give it the wrong key, it'll probably just fail. So I just won't do anything if this fails, but if it works, then I'll just print out the message. Probably should have picked a smaller example, but let's see. A billion's not too awfully big. We might, let's print every 1,000 or million or something. If I mod a million equals 0, system.out.println I times 1.0 divided by the key size times 100. There, that'll tell us what percent we're done. I think that is it. Okay, so obviously I'm not using multi-threading here. I'm just trying to get an idea for how this is going to go with a single thread. You should always get things solved single-threaded before you try to get fancy, right? All right, it's getting a bad padding exception every single time. And I think that's something I'm doing down here where I'm printing the stack trace. I just don't care. So I'm going to get rid of that print stack trace. And also that one. I probably should comment it out, but here we go. We'll try this again. Oh, okay. Actually, I'll tell you what I'm going to do. These methods, I'm going to redo these methods. These methods will assume that whatever's calling them is going to take care of whatever exceptions, and for now they're just going to throw all exceptions. So these functions don't have to worry about, they just assume everything's going hunky-dory, and then if anybody else wants to catch those exceptions, they can. All right, I think that's gonna work for me. So what was happening was it caught the exception and it seemed like it was working fine. It gave me an empty message, and then I printed an empty message, and that wasn't very helpful at all. All right, so here I'm getting quite a few messages. Some of these are going to fail because of other issues, but occasionally it works, but it doesn't know that that's not the message I want. So what I need to do is check to see if that message is is legit. So I'm gonna know that the beginning of my message starts with V. So I'll be like, hey, if message dot contains, or starts with would probably be a little faster, starts with the squirrel. Then I'm going to print out the message. Okay, this is going pretty slow. Not completely unexpected. So I'm 1/1000th of the way done. 2/1000th of the way done. Okay, so I could probably pick a little bit faster. Let's make it 100 times faster. I think that'll be good for this example. So that we'll have to have it go through 10 million keys. I don't have to tell you that cracking at this rate is pretty dang slow. We can do all sorts of things to speed it up, but that's not the point. We're just going to we're just trying to show you how you can parallelize things. Okay, for this to work, I need to get a new set of encrypted text. So all right, it needs me to, well, let's just throws exception. All right, so let's try this again. Well, apparently somewhere between 0 and 10% was the squirrel has landed. That's can't help random chance. Let's try this again. No, I'll make it a little slower. How about? Anyways, we know that it works now, though, so that's a bonus. Okay, so I'm gonna take this and paste it here, and comment out that, and comment in this. All right, and I can get some more often updates. Rounding errors, or not rounding errors, but floating point precision. All right, this is slow, arguably slow. So I think we kind of have the cadence of this. So the question is, can we break it up and go faster? And I think the answer is yeah, definitely. So let's just do that. So, so whenever I set a custom thread, I will need two things. I'll need to know what I'm decrypting, and we'll need to know, we'll know what key it needs to start with and what key it needs to stop with. I'm using longs just in case. I think ints would be fine here, but all right, this die encode equal encode. Okay, there we go. So we have a custom thread, and now our run needs to just go through that, what I just did. So so I'm just gonna copy and paste this down here. Okay, so a key is we're gonna go from start to stop. and this will give us a percent on the whole side, assuming I feed it key size. What do I want to do? Let's just figure out what percent we're through this. So this one will be, so I'll still want to print the same amount so we can get an idea. And here I want to print like what thread ID and what percent it's done or something like this. So you guys have an idea of what's going on here. Okay, so to get the percent done, we're going to say the I minus the start. That's how far we've gone. Divide that by the stop minus the start. That's the range. All right. Make that 100. That'll give you a percent. I'll need to get the my current thread ID. So thread Java. I think it's really easy. It's like get blah 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 blah. Get ID. Bam. Gives you a long. Or get name. Gives you a string. We didn't name this one. I'll just do the ID. But yeah, you can name this one. This one's the file reader, and this one's the file writer. Like you can make it a lot easier. And there's you can then once you name them, you can like stop a thread and pause one. You can do all sorts of interesting things. But here I want to print this dot get ID. I think it's a small d get ID. Yeah. Get ID plus let's do a fancy print. All right, so the fancy print we're gonna do is thread dash percent D is some percent, so this will be percent F, but I want 2 decimal places, so I'll say .2 F percent done, and put a new line character. All right, I already closed that off. I think that fancy print will work. Okay, so we're cooking. All right. Okay, so if we have the key size, I don't need random anymore. Okay. Okay, so I have a key size. That key size tells me how much work I have to do, and I have to separate that out into chunks. So I kind of need to know how many threads I want. I'm just going to make that a parameter, and so you can see how I can just like change a number and then change how many threads I deploy. So num threads, I'm going to start with 4. Well, we'll start with 2 and then see if I can improve beyond that and see if it's worthwhile. Okay, so I'll say for int I equals 0, I less than num threads, and then I plus plus. All right. So inside here, we're gonna just do this. So we'll make a thread. I could add it to an array, but I could just go ahead and start it. I don't, in this case, I don't need to keep track of it. And then I can just start it. No big deal. So I do need to feed this encrypted text to it. All right, so Okay, so I need to give this, and I need to start at I times the key size divided by the number of threads. And this next one is going to be I plus 1 times key size divided by number of threads. So there you go. And this will work int division wise. This will even if number of threads doesn't divide evenly into key size, I believe you can I'll leave that as an exercise for you guys to make sure that this is going to separate it into the right chunks. But there we go. All right, Java missing format. I think %d is the wrong thing for a long. Printf long. So LD. I don't know. We'll try it out. I don't usually fancy print with longs, so there we go. Unknown format conversion formatter. Okay, I'll tell you what. Thread. I'll say %s. And I'll get name and see what that gives me. Okay. Oh, there we go. I had an extra %. Oh, because % signs are special. Do I do a /%? Is that how I do it? Or do I do a %%? We'll figure it out. I think it's a %%. All right. Conversion. What is it not like? LD D okay, I don't have a side-by-side comparison for how fast this was going compared to last time, but it seems like it's going marginally faster. I guess the real test is to see what kind of CPU usage I'm getting. So right now I'm getting 100% of my frame recording. Recording this is taking 20%. Chrome is taking 20%. I think there's this weird thing that AutoCAD has installed that like occasionally will pop up and start taking 20% of my will take all my processor and it'll just run my battery down. I need to track it down and kill it. Okay, so I'm using 50 some odd % for this now that I've freed up, and it's and there's technically 3 threads, so that's not too weird to have that going on. So that tracks. And we haven't solved it yet, or have we? feel like we just have to watch it at this point. Ba-doo-ba-doo. Okay, I'm going to start timing now. We're at 30%, and we're pretty much at 6 o'clock with 40 seconds. All right. I'll pop back in here, and once we hit like around 66. I really need that shirt that says I'm not slacking off, my code's compiling. Well, I have one, but it's kind of ratty, so I need to get a new one. I've gotten fatter since then, too. All right, we're coming up on 50%. Like, the chances are we'll find it soon. I mean, you could always find it way at the end, who knows? Okay, anyways, if you look at the IDs, it says thread 12 and thread 13. So apparently it just picked some random IDs. I don't know if it'll always be like that, but there you go. All right. Once I get to 66 or so, I'll have covered a third of the time, and so I can have a really good estimate for how long it takes to do the whole thing. Okay, so we're at 2 minutes right now, which is pretty close. Okay, so we're going to take approximately 6 minutes to crack this, and we just cracked it. Okay, well, at most 6 minutes. So 3 minutes is the average cracking time. And it just depends on how we split this up and where the check is. So that's all there is to it. So, so 6 minutes is our mark. That's with 2 threads. I think that's faster than normal, but let's crank it up to 4 threads. I hesitate to do this with this while I'm recording because that's taking processing power by itself. But, you know, you only live once. Let's go. Bam. All right, we got 12, 13, 14, 15. So apparently the first thread I make is going to be 12, at least on my system. I don't know if that's always going to be the case. The percentages are going up much faster, obviously. Let's say we started at we'll start it at 6:04. See how long it takes to do 10%. Okay, 10%. We're at 6:04. Let's see how long it takes to get to 20%, and then we can extrapolate from there. All right, it took us 30 seconds to do 10%, so times 10, 300 seconds divided by 6 is going to be 5 minutes. 5 minutes does not sound that much faster than 6 minutes, but it is faster. Of course, we don't have that much more processing power, so that's kind of in line. So now we're at 100 CPU. We went from using 50% of the CPU to using 83%. So that's like right in line. Basically, all this lets us do is use 100% of the CPU. It's not magical beyond that. But so if you have a process that if you're using less than 100% of your CPU, then you must be like letting the system just sit there and waste processor. So throwing some threads on there can help. So killing that. But in theory, you can put 20. It's not going to kill anything. It's not going to hurt. There you go. All of those threads are going to have to fight for resources, and so once they all went to 2% as their first step, and then 4%. This does look like it's going maybe a little faster. I don't know. We're already up to 6%. All right. It was at 10%. It was about 7 seconds in. And they're already getting separated. Some are as low as 10, some has 16% done. Okay, we've hit 20%, but anyways, it takes, maybe this is marginally faster than the last time, but it's kind of hard to tell. Let's see if we actually see, let's see if it says the squirrel has landed at some point. That's the real test. Okay, while we're waiting for that, on the server side, you guys don't need to thread. You're just going to have one thread, and each of the Docker containers you have are going to be given one CPU, and so you don't need to thread to use more of that CPU. We're going to just make a bunch of different Docker images of your thing and run them on a lot of different servers. So anyways, I have that. Well, anyways, there are 64 cores that machine has, and each VM has 2 cores. And whenever I run Docker on top of it, it has, it only allows you to use one of those cores. Anyways, long story short, in theory, you could run two Dockers on each thing, but I'm just going to let you have one, and then so you can go 32 times faster than running on one core, and we'll just make it where I don't have to worry. Like oh, there we got it. Squirrel has landed. We can we can let other people use the other core, so that way I don't have to worry about scheduling. In theory, you know, you guys could all use it at the same time, and then you guys will fight for CPU resources. I'm not going to worry about that too much. I'm going to expect that most of the time you guys won't be fighting. So anyways, blah, blah, blah. There you go. That's some threading. I'm going to go back down to one core, and I'm going to get, I just want to get a quick estimate while I'm here for how long it takes to get this done. So I'm going to time 10% and then see how that compares. And I'll look at, and we're only using 30%. So that should be slower. It must be slower. Yeah, this is definitely slower. We're looking at over 10 minutes, where in the other one we got it down to under 5 minutes. Yeah, we just hit over 10 minutes for the average amount of time. Yeah. All right, I like it when demos work out. So I'll share this with you guys. So I'm going to use the same encryption decryption technique that I did here. It's by far not secure. I just found some simple code that would be easy to package up and send to you guys. I'm missing salts. I'm not using full keys. This AES is not the most secure anymore. There's lots of things I'm not doing right, and I'm not caring about those because that's not the point. So, and it also depends on what you guys have on your computer. Different instances of Java have different things. I think this is old enough that it should be easy to get on all the different machines. So there you go. So hopefully that makes sense. Threading's very easy as far as the way we're going to do it. You just start a new thread. You just make construct a new object which has whatever instance variables, and you tell it to start, and it will have a run method. So here's just your custom object. It extends thread. You can do whatever you want with the constructor. It can have whatever other methods it wants, but the important one is a run method, and it does whatever you want. And concurrency is a problem, so what I would suggest is you just tell it what you want it to do, and then it'll go off and do it. And to report back, you can do a print. So again, we haven't covered packaging up your things in Docker, but when you do, that doesn't need to get multi-threaded. The only thing that you might need to multi-thread is the one that's going to coordinate talking to all 32 servers. So in this case, you would start up 32 threads, one for each of the servers, and so you'd have to. So what I would do for that is I would give it the encrypted text. I would tell it what server, IP address, and then what part of the work you want it to do. And then down here in the run, my voice is breaking up. Down here in the run, what you're going to do is you're going to go to that. You're gonna loop, and you're gonna do socketing stuff with that server. So you're gonna connect with it. You're gonna send it you're gonna send it some work to do. It's gonna send you an answer back, and then I'd probably just connect again and send it some more work to do, and it'll send you some more. It'll send you an answer back. So you have to incorporate some socketing in here, and you have to. I would prototype that locally and make sure that's all working, and before you even worry about Docker and getting it all packaged up. So, anyways. Hopefully that helps get you started. And again, I'm not requiring you guys to do this. I think it would be fun. It would be fun for me if I was in your guys' place. I know you guys have responsibilities and summer's coming, and if you guys have the cycles and you want to learn this, I would say learn it. I think this is very valuable information. So, anyways, peace. Be safe.